Okay, thank you. So what I'll do today is I'll explain how basically very similar methods lead to a fairly complete description of the birational geometry of moduli spaces of sheaves. And again, this will be everything over K3 surfaces. And I mean, all my own work on this is joined with Emmanuel and Macri. And so the setting today will always be that X is a smooth projective K3 surface over C. And let me first make the connection to yesterday. Right, so yesterday I looked at this moduli space that was the compactification of the relative Picard variety. So here I had a K3 surface of Picard rank 1, and I had picked a number D less than or equal to its genus minus 1, and then I look at this moduli space 0H D plus 1 minus G. This compactification of the Picard variety, and inside there I have the locus of line bundles with global sections. Right, and so what I did yesterday, I basically described the geometry of this locus as a union of Grossmanian bundles. So Grossmanians of R plus 1 planes in a vector bundle, and this vector bundle is over another moduli space M of WR, where WR is given by V minus R plus 1 times the Mukai vector of the structure sheaf. Right, and actually let me also, this is probably right, so this is the Brill-neutral locus. And let me, actually, this is a good time to mention that this description had already given by Markman somehow with, I mean, not with wall crossing methods, but with vector bundle methods, basically making these Lazarsfeld results more precise. And so what we'll see today is that, I mean, what the results today will imply is that there actually is a birational contraction from this MH of V to some singular variety that precisely contracts this Brill-neutral locus, right, with exceptional locus equal to the Brill-neutral locus. Right, so in another way, I've already started to you with what I did yesterday. I've already started to describe to you the birational geometry of this moduli space. Okay, so let me say a little bit more precisely what the goal is for today. So what I want today is for an arbitrary moduli space smooth moduli space of sheaves on a K3 surface. I want a description of the birational geometry that both contains statements like this, but also the global picture of the movable cone and so on. Right? So given V in the Right, let me remind you, n of x was the algebraic cohomology. Primitive. Right, so I'll always assume that V is primitive. One can actually also look at the O'Grady cases, at the O'Grady case. So where V is twice a primitive class of square 2, and that was done by Kira Meekan and Zhu Zhang. But I won't focus on that. Right, and so what I want is complete description of the birational geometry. And what an answer should contain? Well, first of all, I mean, how do we find birational models? Where we look at movable devices that are not nav and try to find the corresponding model where this becomes ample. And right, so if I just want something like a list of all birational models, then of course the way to do that is the description of this decomposition of the cone of positive divisors. Right, we want a chamber decomposition. Of the positive cone of M. Of here, so I'll let M be this moduli space of Giesecker-stable sheaves of Mukai vector V. Right, so the positive cone inside here, just a neon-Severi group. Right, and let me remind you that this already appeared in François' talk, that the neon-Severi group is just isomorphic to V perp inside n of x. Right, with the restriction of the Mukai form on V perp becomes the Bovil-Bogomolov form under this identification. Right, and so the positive cone has this chamber decomposition. First I have the movable cone somewhere in here. Right, so this is the movable cone generated by movable divisors, and then the I have a further decomposition has already appeared in Katja's talk, given by further planes, and then the Neff cone will be some chamber in here. And all the other chambers of the movable cone correspond one-to-one to birational models to mark birational models of M. Right, so in particular, I mean, with this chamber decomposition, this would give me inside here the movable cone, and inside here the Neff cone. But I also want an, so for every Neff but not globally generated divisor, for every, and so in other words, for every birational contraction morphism, right, so these are associated to walls of the Neff cone. I want to know the geometry of the exceptional locus, similar to the Brunner. Right, and so this is my goal on the one hand, and I want to do this by describing wall crossing, and of course that's a goal by itself as well. Right, so consider now M sigma of V as V is still my fixed class from above, and sigma in star of x varies. Right, and then again, then I also have a chamber decomposition like this, where as sigma varies within one chamber, nothing happens. When it hits a wall, I have strictly semi-stable object. When I cross the wall, the moduli space changes. And right, so we want a complete description of these walls, of this set of walls. And I mean, what connects these two? Basically, I mean, there had been earlier observations, starting with work by Akara Bertram, that, I mean, some are following the wall crossing here exactly. If you look at the associated moduli spaces, they exactly follow the minimal model program here, right? So by right. I mean, observations that this induces a minimal model program. Right, so here I mean minimal model program for a pair where I pick this variety together with the movable divisor, and then the minimal model program would try to make this movable divisor an F. In other words, construct a birational model where this is ample. Okay, so this really started with Akara Bertram. Questions? And it turns out there is a semantic connection between these two. And so this is the one ingredient that I won't say much about, but it's of course it's absolutely crucial. It's the what we call the positivity lemma. So, and let me state it as follows. So, given if S parameterizes a family of sigma stable objects of class V. So let me first say what this means. Right, so this just means that I have an object E in the derived category of the product, such that when I take the restriction over a closed fiber over to the fiber over a closed point in X, right? So this is now an element in D of X, and I want this to be sigma stable of class V. Sorry, so let me do it for semi-stable objects. This is actually fairly crucial to allow semi-stable objects. Then the claim is that to this situation one can automatically associate an F divisor on S. Then get an F divisor L sigma on S cross X on S. And so maybe let me also write down the formula just to stress that there are no choices involved, right? So when one has a Giesecke moduli space, then of course one can get many ample line bundles on this from GIT, but one has to make some choices. And so somehow the point here is that the choices are automatically made for you by the choice of stability condition. And so just to stress this point, I'll write down the formula. So for this formula, let me assume that Z of V is equal to -1, just some normalization, which I can always achieve by rotating the stability condition. So this is not a big assumption. Right, and so if E cross X, S cross X, S P xq. So what I do is I take E restricted to C cross X, E restricted to the curve cross X, I push it forward to X, and then I take the imaginary part of the central charge. Right, so it's completely determined by the family, and it's easy to check that it doesn't change when you tensor the family by a pullback of line model from S. So it only depends on the objects that S is parametrizing. And then the only ingredient, right, and then the central charge somehow gives you the essential linear algebra data to define this class.
How do we know it's not?
I mean, that's the claim of the lemma, yeah. And so that, I mean, that proof needs some more ingredients. So, I mean, that needs a bit of a structure of. I mean, for that, I'll have to take the T structure I started with on X and have to construct a T structure on S cross X, and play with that. So, I mean, I won't have time to explain it in detail, but let me make the result more precise, right? So this is NF, so I claim this is greater or equal than 0. I mean, basically where this comes from is, again, it comes from the positivity assumption on the central charge. Namely, what one can prove using this Abramovich-Polishchuk setup is that after tensoring by some ample line bundle pulled back from S, this push forward is actually in my heart of the T structure. And so then this positivity directly comes from my assumptions on the central charge. And so moreover, so not only is this non-negative, so I can also precisely say when this is equal to 0. Namely, if C parametrizes S equivalent objects. So let me. Which means, right, so all EC for C in C have a filtration with filtration quotients that are stable of the same phase. And so right, this is just the Jordan-Hölder filtration, so far I haven't said anything. And the point is that the filtration quotients are independent of C in C. Right, so in a GIT setup, this categorical notion of S equivalence is really the same as the GIT notion of S equivalence. So I mean, another way I could have said this is that these objects have the same polystable replacement. If I replace them by a direct sum of stables and kill the extension classes, then they all become the same. So in other words, I mean, this says that C parameterizes in the coarse moduli space, all these objects become identified. Sorry? Yeah, it's a numerical Cartier divisor class. Yes, yeah. Yeah, so no, it's a divisor class, right? So L. Yeah, maybe let me make this precise. Yeah.
Do you have some assumptions on this?
Basically no assumptions. No. Right, I mean, numerical Cartier divisors, of course, you can basically always define, and then you always get such a class.
Is it known that the S equivalent class of objects is projective, variant, or something like that?
No, in general not, right? So to prove that you get a projective coarse moduli space, the approach now is really take this NF line bundle and prove that it's globally generated. Yeah.
Okay,
That's
so this is unknown in general. So that's okay. That's an approach to this problem.
Exactly, yeah. Right. So so let me Right, so let me again make this corollary more precise. So if I have a chamber C in the space of stability conditions, then, I mean, as I said, the moduli space doesn't vary when I walk around in this chamber. So let me call it just MC of V. So this is a fine moduli space for points in the interior. All the objects are stable, so this S equivalence can never happen. So this has a family of, I want to say ample, but all I know is that they're positive on all curves. And then just by continuity, for points on the boundary, I also get Neff classes. But one can also see this. If I take this moduli space and now consider it as with respect to a stability condition on the wall, then it's still a family of semi-stable objects with respect to this stability condition. So I still get a Neff divisor, and I know precisely which curve get contracted by this Neff divisor if I knew it was globally generated. Right, so then I get, and so positive divisor classes for sigma in the interior, and Neff divisors for sigma in the boundary. Right, so in other words, I get a map from the closure of the chamber to the Neff cone of this moduli space, MC. Okay, more questions at this point? Right, and so, so in other words, if I know one chamber in the space of stability condition, I already get a little bit of this picture, right? I know at least part of the Neff cone. And to get the full picture, I also want to somehow continue this picture as we cross a wall. And so the first result here is that, so in the setting for K3 surfaces, is that every wall crossing, right, so here I have a wall, and so here's sigma east on one side of the wall and sigma west. So I feel like since I'm German, a wall has to separate east and west. And then the claim is that such a wall crossing induces a birational map from M sigma west to M sigma east. Right, and these are all these are all holomorphic symplectic varieties. So in particular, this birational map cannot contract or extract any divisors. And so in particular, this means that I can canonically identify the Néron-Severi groups. Okay, and then I'm ready to state the main result. So let me now Right? I mean, in particular, I mean, for different chambers, I have maps to nav cones of different birational models. And since I can identify the neon-Severi groups, I can identify. I mean, I can all think of this as happening in the neon-Severi group of one fixed moduli space. So let me fix a base point for that purpose, and let me assume that it's generic. So by which I just mean that it's not on a wall, and then the right, and I have these maps L for each individual chamber C. So, and the claim is that they glue to a continuous map L from the space of stability conditions, or maybe I should say from this connected component that we started with, to the positive cone, maybe let me say to the neon-Severi group of this fixed moduli space, tensor R, with the following properties. Right, and so the first property is, that's really the important one, is that it's compatible in the following sense. Right, if I take a stability condition, then m sigma of V is precisely is the birational model corresponding to L of sigma. Right, and I mean, for this to even make sense, maybe I should have switched the order of the statement, is I should describe to you the image of L. So the image of L is almost equal to the movable cone. I just have to, I mean, the movable cone might have divisors of positive square, and I have to take this out. So in this picture, I just have to take out the three corners of the blue triangle. But other than that, it hits everything in the movable cone. Right, and maybe the crucial part is that one can really use this. So one can use this to precisely describe the wall crossing in stub dagger of X plus all these this chamber decomposition of the movable cone. Okay, and so so basically the methods follow. They're really similar to what I explained yesterday, right? So I mean, let's say let's start with just trying to understand this chamber decomposition here, right? So what can I say about this chamber decomposition? Well, if I have sigma on a wall inside stub dagger of X, then I mean it's easy to see. So let me put quotation mark in easy and explain the quotation marks in a second. Well, it's easy to see that from this it follows that V can be written as a sum of A plus B, so that Z of V and Z of A all point in, and Z of B all point in the same direction. Right? So here I have Z of V, then Z of A and Z of B have to lie on the same ray. And with A squared comma B squared greater or equal to -2. Right? So where does this come from? This just comes from the fact if I'm on a wall, then I have a strictly semi-stable object. Look at the Jordan-Hölder factors. And then the crucial ingredient here, and that's why the quotation marks are here, is then the theorem that the moduli spaces are non-empty if and only if the squares are greater or equal than -2. Right? So this really comes directly from knowing which moduli spaces are non-empty. And it turns out that one can also prove the reverse inclusion, the reverse implication. Right? And some of the reverse implication is fairly easy if I have stable objects with class A and B along this wall. Because then I can do the same trick as I did yesterday. Just form an extension. Right, if I have A in sigma stable of A and B in sigma stable of B, then I just form any extension of this form. And one can show that such extensions exist and that they become stable on one side or the other. And so the tricky part is when the stable locus becomes empty. And then one has to analyze where this can come from, and this always comes from some. This always is due to some spherical object. S. So right, by which I just mean a simple object, a simple rigid object. Destabilizing all of M sigma of A. Right? Something simple would be a simple example, if I hadn't made this degree assumption about D in my example yesterday, then all line models have a global section and they all can become destabilized. And now, of course, I need to use some more derived categories technology. With such a simple rigid object, there's an associated autoequivalence lying over the reflection. Right, so V of E S squared. This is in this. This is also a class that's proportional to A and B. Right, so again, I have to use this rank 2 lattice. I take the lattice generated by A and B and its iteration inside the algebraic homology of K3. And basically, that's the tool that I have to use all the time. Right? So inside this contains all the Mukai vectors of objects whose central charge automatically align with Z of V along this wall. Right, and so such a S on the one hand gives me a reflection on this lattice and the derived autoequivalence, and one has to play with this and show that this still works. Okay, and now and basically the positivity lemma then says that this corresponds to a wall in the movable cone if and only if one can vary the extension class in star. Right, so if I can vary this extension class, then I have a family of semi-stable objects that become S equivalent along this wall, and so I have rational curves that get contracted by this divisor. And I mean, of course, all this is a little bit simplified because often the Jordan-Hölder filtration, even of a generic object that becomes stable, is longer term than 2. But I mean, that's essentially. I mean, that's really the essential content of what's going on. Okay, any questions so far? Right, and so I promise you that one can use this to deduce the chamber decomposition of the positive cone, and so let me state this result. Right, the chamber decomposition so I could also state the result about the positive cone. I mean, the chamber decomposition of the positive cone into translates of the movable cone, which is already, I mean, which one can reprove using these methods, but which was proved earlier by Markman. So instead, let me give you the decomposition of the movable cone into Neff chambers. And so this is given by. And so let me write it in terms of this identification of the Néron-Severi group of M with the orthogonal of V. Right? And so the statement is just that this is given by all hyperplanes of the form V perp intersect A perp for all A in the algebraic lattice of the K3 with A squared greater or equal than -2. And 0 less than or equal to V, comma A less than or equal to V squared over 2. Right, and so where does this come from? I mean, if you do the computation, then this inequality actually directly translates into, I mean, more in this, this translates into V minus A squared also being greater or equal to -2. Right, so this equality really directly comes from V being a decomposition into two classes of square at least -2. And then, I mean, I would have to explain a little bit more where this comes from. This really comes from analyzing what this condition means. Okay, and so one can extend these results to all I mean, this description one can extend to the whole deformation type, so to all reducible holomorphic symplectic varieties, deformation equivalent to the Hilbert scheme of points on the K3. And one can either do this via twistor deformations, so really I mean, exactly with the ideas that Katja explained yesterday in this work by Amarik and Verbitsky. In this situation, this was done by Mongardi. Or, I mean, deforming rational curves. And that's the approach we took in. So this is a paper with Brandon Hassett and Yuri Chinkel. I mean, here the basic observation is that if you have an extremal rational curve, then one can knows enough about its normal bundle that one can control its deformation. And in particular, it deforms along with the variety as long as its class remains algebraic. And that's why one can do exactly the same. Exactly the same description holds in this whole deformation type. You may wonder what this n of x is for an arbitrary hyperkaehler of this deformation type. Well, it turns out that this is really, making the global Torelli precise in this result. Markman showed that every hyperkaehlerity of this deformation type has a lattice associated to it that's equivalent to the K3 lattice when it's a moduli space. Okay, let me also explain one other application. Right, so what I've done so far gives you all the birational contraction morphisms, but it turns out that one can actually use this wall crossing to really describe all the contraction morphisms. So what is missing for an irreducible holomorphic symplectic variety, whenever you have a fibration, so a morphism to something lower dimensional with connected fibers, then it's automatically a Lagrangian fibration. And there was a conjecture when this exists, and so let me give one version of this. So there's a birational version and a version on the nose. Let me just state the birational version. So if there exists in the Néron-Severi group with Boville-Bogomolov form equal to 0, then MH of V is birational to a Lagrangian fibration. Birational. Right, and this was conjectured in print by Justin Savon, Heubrechts, and Hesse-Schinkel, but it's really early. It was known as a conjecture, was known to people much before. And what is the idea here? Well, this D corresponds to a class V W in V perp with W squared equal to 0. Right, and then of course I look at the associated moduli space. This is a K3 surface that's derived equivalent to my given K3 surface. Right, and so if I take, I know that MH of V is isomorphic to a Bridgeland stability condition in the derived category. And once I formulate it like this, I can of course apply the Fourier-Mokai transform and reinterpret it as a moduli space on Y. Right, so this is I can pull back the stability condition, I can pull back the class, and the moduli space is the same. And now this is a moduli space of rank 0 objects. Right? This is very easy to see because W and V pair with 0, and W goes to the class of a point under this derived equivalence. Right, and now what do? I just look at wall crossing on Y. Right, so I know I'm somewhere in the space of stability conditions on Y, so this is a picture of stab of Y. And somewhere here I have this Giesinger chamber. Right, and so all I need to prove that phi upper star sigma is in the same connected component, and this is not so hard. then I walk from here to here. Right, so here I get some mh prime of phi upper star v. But this is so here, this path induces me a birational map. M phi upper star sigma of phi upper star v to this Giesecke moduli space. But since phi upper star v is rank 0, this is exactly the situation I had yesterday, right? This class is 0 something something. So it's ranked, it's a moduli space of torsion sheaves, and it has a map to the underlying linear system. And that's really that's the proof. Right, and one can also, make this a little bit more precise and show that when D is Neff, then one doesn't have to change the birational model, and MH of V itself has a Lagrangian fibration. And let me also say a little bit about other surfaces. So in a way, the case of K3 surfaces is simple, precisely because we have these strong results for non-emptiness of moduli spaces, and so even for P2. In a way, this was, this is harder, and in some aspects it's harder, and there were many people working on this Akara, Bertram, Koskun, Risenga, Wolf, and then really it was finished in a paper that's about to come out by Chun Li and Xiaolei Zhao. And why is this even possible? Because for PT, again, one has an answer for which moduli spaces are Giesecke stable. But the answer is much more complicated, so it's classical work by Drosili and Le Portier. One has to then be even more precise and say for a given Bridgeland-stability condition which moduli spaces are non-empty. Again, this is the answer is yet more complicated, and then one has to do this analysis of when precisely do I have walls. And one can also do Enriquez, and that was due to Howard Noer. But again, here the results are not quite complete, again, because for Enriquez we don't have a precise knowledge which moduli spaces are non-empty. Okay, let me stop here for today. Thank you.